Hello, everyone. My name is Sam Campbell. Thank you for that lovely introduction there. I'm a first-year PhD student here at UQ. Started in July, and my project in Brian Fry's lab is kind of looking at scorpions as a whole and taking a couple different angles to kind of investigate different aspects of scorpions, be it their kind of venom function, be it morphology, and hopefully a little bit further down the line, looking at their epidemiology as well, which you might see a little bit of here. So this project, however, is focusing on antivenom, in particular looking at Mexican scorpion venom and taking the context of how effective is the antivenom that's produced within Mexico against that venom, because it's a severe public health problem and it's something that really needs a lot of research to look at. But to begin, just kind of summary talk about scorpions themselves. So scorpions are a very unique arachnid. They're around 450 million years old is when they kind of originated as aquatic organisms, actually. And they've radiated pretty globally on all continents except for Antarctica. And they've got around 2,000 species. That's kind of what we know about. There's probably a much greater diversity that are unknown. It's just because our kind of characterization just isn't quite there yet to cover all of them. They have a very unique morphology. As you can see here, they kind of possess these two key weapons, as I like to kind of think of them. So they have these oral appendages at the front. These are called pedipalps. They're a pair of claws. And at the back, they have this large metasomal tail, which is topped by the kind of venom-producing gland in the telson. So that's where they sting. They can pinch, and it is a defensive behavior known, but the telson is kind of the main kind of aspect of their kind of function and what they're really known to be using. So of those 2,000 species, there's actually fewer than 50, probably around 30 to 40, that are considered of significant medical importance. And almost all of those exist within the family Euthids. And that's where this little guy here comes into play. So this is the centroidy scorpion. This is commonly referred to as a bark scorpion, and it's found throughout central Mexico as a particular kind of hotspot within central Mexico. And what I'm just for back a little bit, medically important is a phrase that's going to come up a couple of times. So medically important, by my definition, and what is considered the definition, is as kind of a scorpion from which envenomation has potentially life-threatening or fatal systemic effects within your physiology, and the likelihood of requiring clinical treatment is very high. But to come back to the centroidy scorpion, these are particularly known within Mexico. And to briefly just come across this, the reason that we want to care about this is that scorpion envenomation in Mexico is very high. So on average per year, Mexico has around 250 to 300,000 envenomations from scorpions per year. And that's particularly concentrated within this central region of Mexico here, which has in the last 10 years seen around over 1 million envenomations. Now, when you compare that to the global estimated annual envenomations, which sits around 1.4 million scorpion envenomations globally, you really kind of focus in on how much of a significant public health problem this is within Mexico. Now, despite that, or rather luckily, it's not frequently fatal within adults. There's on average 30 people per year who die from scorpion envenomation in Mexico. But part of that 30 per year, and actually a majority of it, are at-risk groups of individuals who are dying, and in particular children. Within the age groups of 1 to 4, scorpion envenomation is the 7th leading cause of fatalities, and that's higher than conditions such as tuberculosis and rickets. So it really kind of highlights that this is a major problem within Mexico that's often overlooked within other countries just because it's not necessarily as visible. Luckily for us, this is not a new thing in Mexico. It's been something that they've dealt with for a very long time. And as such, they've developed good data to track it. And they've also been real pioneers in the development of antivenom technologies, actually dating back to the first scorpion antivenom being developed in 1905, which is kind of, I think, like 10 or 15 years after the very first antivenom even was created to begin with. So what's causing these kind of severe envenomations? Well, scorpion venom is a kind of diverse, complex mix of bioactive peptides, enzymes, neurotoxins. And they're using these to create an overwhelming neuroexcitatory syndrome to effectively shut down their prey. They use it in it's not just prey though, they can use it in defense. And obviously we all know about the promenade de deux, the kind of sexual contest to which scorpions are very well known. But of the venom, the real components that I particularly care about, and in terms of kind of medically relevant context are neurotoxins. The scorpion venom is a primarily neurotoxic venom in its action, and there's a couple of different groups of toxins that, in terms of their are characterized by their physiological targets that are particularly interesting. These are sodium channel toxins, that's alpha and beta sodium channel toxins, they're kind of two different groups, potassium channel toxins and calcium channel toxins. The net result of these toxins within these venoms are you experience a kind of overwhelming and really systemic and hyperactivation of your sympathetic and parasympathetic nervous system, which also triggers your inflammatory cascade, such that when you have systemic envenomation from one of these medically important species, you present with some very severe clinical symptoms that can be associated with a range of different pathologies. So within your cardiovascular system, you could expect to see symptoms such as arrhythmia, tachycardia, heart failure, pulmonary stroke. And then on the more neurological side of things, you would expect kind of symptoms such as paralysis, both flaccid and spastic paralysis. And you also get kind of hypersalivatory syndromes and a range of gastrointestinal complications that can come along with that as well. But of those species within Mexico, there's an approximate 200 in terms of biodiversity. There are 21 species that are considered of significant medical importance. Now, we know through previous studies, that antivenom has been shown to be effective in treating the venom from the envenomation from centroides scorpions in Mexico. However, because of identification problems, and it's very hard to know what scorpion has stung you, these studies have never really been able to account for which scorpions are doing the envenomation, and then thereafter which ones are being negated by this antivenom activity. It's very hard to identify a scorpion effectively, but even for some experts, you can kind of really to get under a microscope effectively to properly identify real species. And so in consideration of that, and also the fact that commercially available antivenoms are made from just a handful of immunizing venom species, so say just 2 to 4 species of centroides venom, you have to ask the question of, are these antivenoms broadly effective against all of these different medically important species? And unfortunately, it's not really something that's been considered before. And it's just something that I think that we feel has been somewhat overlooked, because if you look to the world of snake antivenom research, and then we have seen time and time again that effectively species to species variation in venom has caused a massive inability of particular antivenoms to negate that venom activity and can be potentially life-threatening. So that's the kind of context of why we want to look at this antivenom activity. But to do this, we have to kind of identify some of these main physiological targets. And that's where voltage-gated sodium channels come in. So voltage-gated sodium channels are a kind of classification of ion channel that are found predominantly throughout the body. And there's a range of different kind of skeletal of different functions and different tissues in which they are solely expressed. So their key role within excitatory tissue is that they initiate and propagate action potentials that leads to kind of muscle movement down the line. And because of this and the physiological effects mentioned earlier, where you see cardiological issues or you see muscular differences in different muscular pathologies, we decided that the 2 targets we'd be particularly interested in terms of kind of correlation would be to identify skeletal muscle and heart muscle targets. And that's where these 2 subchannels come in. So there's NaV1.4, which is a subchannel that's only expressed within the skeletal muscle, and NaV1.5, which is a subchannel only found within cardiac muscle. And this kind of comparison of these 2 targets would allow us to make kind of, I suppose, decisions about which venoms might be targeting preferentially, or which toxins could be targeting preferentially those, and which could be related to those key kind of physiological symptoms. But how do we actually want to look at that? Well, the answer to that is an electrophysiological assay, in our case, a whole cell patch clamp. And to do that, we use this little machine here. This is a Saphion Q-patch electrophysiological assay. It's a kind of an automated liquid handling machine that enables you to do 16 wells of an assay at a single time. And in each of those wells, you're investigating a singular cell. And because of kind of advances in cell engineering, we're able to use cell populations that singularly express one type of ion channel that we're interested in. So we have a population of NaV1.5 expressing cells and a population of NaV1.4 expressing cells. And what this assay allows us to do is effectively clamp it down and we can measure the movement of ions through that cell, from one solution to another solution via these electrodes. And that change in ion concentration, it registers as current. And this effectively represents how these NAV channels are functioning within that population of cells. And that would kind of allow us to effectively introduce venom and antivenom in different ways to check, to almost investigate how that venom is changing the activity of the singular channel. So you can see a kind of little hypothetical visual. It's not necessarily what's happening, but you can see there's kind of binding of the venom to these singular cells, and then there's antivenom floating around. So how we've kind of designed this assay is it's kind of a direct competitive assay, where if we introduce the venom, we know what the venom activity is, but if we then introduce the venom and the antivenom, is there effective binding between the venom and the antivenom to negate the venom activity on these ion channels, and what kind of concentrations of antivenom and kind of concentrations of venom are required to see this happening? And well, the answer to that is a little profile like this. So this is an electrophysiological profile of one of the most medically important species of scorpions. This is Centroides limpidus. So this species here is found throughout central Mexico and is known to be one of the higher kind of, or more rather lower LD50s species. And what you can see here is the phasal state of a NAV 1.4 channel is this saline reaction here, where you see it's rapid opening and rapid closing of the channel, where the influx of sodium ions causes a decrease in the current. So that's your basal state, where your kind of normal function. And as we begin to introduce concentrations of whole venom, this is actually whole venom concentrations, we see that current starts to decrease. And what that's effectively telling us is that this whole venom concentration is able to begin to completely inhibit this channel function. And that's at concentrations as low as 400 nanomolar. We are seeing complete inhibition of this channel function from whole venom activity. So that means within this venom, we get some incredibly potent and high affinity binding sodium channel toxins. And then if we move on to, so this was actually, I believe I said that there's a NAV 1.4 channel that we're seeing. So this is the strongest channel that we've seen binding. And also it's worth pointing out, we have a little PTX tetrodotoxin control, which is just showing that complete inhibition of the channel is being achieved as a control. And you can literally see within milliseconds, you're seeing opening and closing, and then complete inhibition of that activity by the venom. Now, if you then compare it to this one here, so this is a NAV 1.4 screen using the same medically relevant species, you see a very different profile to our kind of venom inhibition of the channel. So this is largely down to the NAV 1.4 subchannel being a PTX resistant subchannel, and it appears that the venom might have some very similar activity against this channel alongside TTX, because we're seeing nowhere near the same degree of inhibition of that channel. So that's a very interesting kind of initial sort of interaction, where we're seeing that NAV 1.4 is very, very highly affected, and it could be possibly linked to the paralysis that you tend to see with Mexican scorpions. Whereas in NAV 1.5, we're not seeing anywhere near the same level of inhibition of function. So it's quite likely that although voltage-gated channels may be a main target within the cardiological symptoms, it's likely that there's some other kind of ion channel interactions that could be the potassium channels going on that are relaying these kind of symptoms like arrhythmia or tachycardia. So what happens when we introduce antivenom? Well, the answer to that is we see almost complete inhibition of that venom channel inhibition. So double inhibition. So you'll see here that the saline reaction is equivalent to the venom concentrations that we've introduced. So this is another medically relevant species. This is Centroides sufficus, and this time against the NAV 1.4 channel, where we see it completely, the addition of the antivenom completely negates any inhibition of the channel function. So from that, we can kind of draw the conclusion that with this venom on this particularly significant relevant target, and with this antivenom, we know it's effective. And this is kind of the core basis of what I'm going to be doing, is I'm going to be using this platform as a way of assaying a broad spectrum of venoms. I'm actually doing up to 12 venoms, and 11 of those are medically important Mexican scorpions, and one of those is actually we're including is a Brazilian species of scorpion, Titius cerulatus, that we're including in the mix, just to kind of see what differences in channel binding you're having and whether or not these antivenoms could be potentially effective against that as well. But this assay is a really kind of powerful tool to give us the real gold standard of identifying what channel activity is being caused by these whole venoms, and thereafter its inhibition by antivenoms. So in my project, I've got 12 venoms that I'm looking at. I've got 2 clinically relevant targets. I've got 3 commercially available antivenoms, 2 commercially available antivenoms, and 1 soon to be, that I'm assaying to kind of check for comparative activity between these antivenoms, where I'm using, and the 12 venoms that I'm using are not, are largely non-immunizing venoms. So it's to kind of test either immunizing and non-immunizing to kind of test whether or not we're seeing the same activity of inhibition by this antivenom of venom activity between ones that are within the mixture that was used to create the antivenom and ones that are not within the mixture that was used to create the antivenom. It's currently ongoing, and I actually think I might have finished the data collection on Monday. So I'm very much in the middle of my data analysis phase. I've got a huge bulk of data to get through. If you can imagine the number of replicates where each of these is kind of measured, each of these data points is about 0.0001 seconds. So a very large amount of data that I'm currently working through and working towards getting to hopefully publish. I can't particularly comment on if we're seeing much differences, but I believe that in one of my venoms, we are actually seeing differences between the antivenoms in the inhibitory function at the concentrations that we're investigating, which would be very significant if it was. The net result of all of this, I suppose I should say, is that we're effectively looking to analyze these antivenoms and say which of them are more effective on a broad spectrum, and thereafter enable better clinical decisions to really treat these this significant public health problem within Mexico, and hopefully make better decisions. If there are any antivenoms that are kind of a broader action, then those are absolutely the ones that you want to have within the clinics within Mexico, because they would be the most significant in terms of dealing with any major problems. So yeah, I just wanted to say thank you very much. Thank you to all of the King Lab, the King Lab who have been significant help in me doing this, because I actually live between both the King Lab and the Fry Lab. Thank you to all of the Fry Lab, of course, who've been massive in supporting me. I wanted to just quickly point out this little guy here. I don't only care about Mexican scorpions. I do like Australian ones as well. This is a little rainforest scorpion I caught up in Mount Crosby in kind of just a little bit outside of Brisbane in Queensland. A very cool little guy. He's not very lethal. He actually uses his claws more than he would his telson, so I felt quite safe handling him. Here are just the list of references for anyone who is interested, and any questions, please let me know.
Yeah, thank you very much, Sam. So are there any questions? If not so, I will start again. And you showed this electrophysiology method where you have the single cell investigated. Is it necessary to know the orientation of the cell? Are the hex cells making some kind of layers where they might have an up or down in the orientation that might influence the outcome?
No, so the voltage-gated sodium channels are kind of expressed on the on kind of universally on the outside. They're not particularly focused in any place and in any chance. Like, we're doing so many of these that it's quite finicky as an assay. So there is definitely a chance that some of the assays that I've had fail are due to the particular part that's being patch clamped is not necessarily expressing or the cell is not necessarily expressing as many of these ion channels on its cell surface. But as far as I'm aware, directionality is not a factor, but there is a whole range of factors that can really prevent an electrophysiological assay from working. It's been a real learning curve as an assay goes, because it's really like to thrown up issues for me, but it's definitely been interesting learning the assay. Yeah, but I don't think directionality is a major issue now.
Okay, and the second one I have is, how much time do you have to apply an antivenom? So I know from the neurotoxic snakes, it's the time is really low, because then you have directly some heart failures or some breath problems. How long is the time after scorpion venom that the medical treatment has to be applied?
So for severe systemic envenomation, particularly within children, it's within the hour that you need antivenom to be applied. So when you initially get stung, the systemic kind of effects don't immediately happen. What typically begins first is pain at the site of the injury, but the systemic ones are a bit slower because that's to go in your bloodstream. And I think generally it's considered that within, like, as with a lot of things, really, it's like the golden hour, your first hour post envenomation is when it particularly matters. But I think within 4 hours of antivenom administration, mostly all of those symptoms will cessate. That's how effective these antivenoms actually are.